Welcome back to this advanced manufacturing and process modeling course. So, we were discussing about the casting and associated transport phenomena based issues, and we have discussed in detail about how we can develop computational fluid dynamics based solidification model to understand the solidification macroscopic as well as microscopic mechanisms. So, as I have discussed with you how we can also predict the viscous evolution, velocity, temperature fields evolution during solidification of a metal or alloy melt, and also I have discussed how we can couple the model with microscopic phenomena such as prediction of grain size, degree of sphericity of spheroidal grains in case of semi-solid processing, and also we have predicted we have discussed about how we can develop models to predict segregation of solute elements, thereby formation of micro as well as macro segregation in the solidified objects. So, moving ahead, we will discuss about the mesoscopic phase field model that has been implemented and improved by our research group. So, where we will also show you how the phase field model works on solidification microstructure prediction, and also predicts the defect generation in the solidified parts, and also we will show couple of case study so that you can understand how phase field model can accurately simulate the microstructure. Okay, so so, these are the different type of microstructure. Again, the example of a typical aluminum silicon binary alloy is taken over here. So, this is a typical dendritic microstructure that is generally obtained by conventional gravity casting, where the cooling rate is much lesser, and also it is basically the solidification front growth rate is higher. So, whereas in case of higher cooling rate, like in case of semi solid processing, like we were discussing the example just in the previous slide when we have discussed about the multi-phase multi-scale CFD based process model. So, you can basically that process model was predicting the microstructural information in terms of quantitatively in terms of grain size, degree of sphericity of the evolving solidifying grains, etc. Whereas, in this case you can actually simulate the microstructure in case of both conventional gravity cast state of the same alloy, and also when you carry out the semi solid processing, and thereby you can achieve spheroidal microstructure in the alloy. Okay, so, a similar example is given in case of a magnesium aluminum gadolinium alloy. So, you can see there again there is a two phase microstructure where the alpha grains are dendritic in nature in case of solidification under 0 T magnetic field, and when there is a magnetic field assisted solidification is happening. So, then you can see that because of the fragmentation of the evolving dendrites, and also because of the promotion of the heterogeneous nucleation, you can see rosette like structure in case of the same alloy, same magnesium alloy. So, so these are the different kind of microstructure we generally observe in the cast parts due to the change in process conditions when the chemical composition is kept constant. So, basically we can see the effect of I would say the effect of process or alteration as well as the alteration of the chemical composition on. So, we can see the effects of these cases, process alteration, chemical composition alterations on the resulting microstructure of the solidified alloy, resulting microstructure. So, you can basically one can predict by developing a accurate phase field model, and thereby it can be, so we can estimate that whether the desired microstructure is achieving the desired quality characteristic in terms of the size, shape and morphology of the grains, and thereby we can tune the process, we can tune the process conditions, process variables. So, all those things are possible. So, this is the importance of the mesoscopic phase field model for solidification microstructure prediction. Okay. So, let us discuss a little bit of detail about the phase field model. So, like in most engineering application, metals are used after alloying with other metals or non-metals, and during fabrication metals undergo solidification process. So, the temperature in solidification process reduces from a value which is above the liquidus temperature or to a value lower than the solidus temperature. If we are talking this in case of an alloy, whereas in case of pure metal it is the liquidus and solidus temperature are same, and in case of pure metal it is signified as equilibrium melting temperature. Okay. So, I mean this is the, we have discussed in detail all those things when we have discuss the casting solidification module of the course. So, this is the case in case of pure metal, whereas in case of alloy there is a freezing range which prevails. Freezing range means the temperature gap between liquidus and solidus temperature are called freezing range. Okay. And also that is also called the mushy zone, when the temperature of the melt falls in between the liquidus and solidus temperature. That is, if for example, if this is the TL. So, say it is say if the TL is somewhere around say 615 degree centigrade in this particular alloy, if I take the example, and TS is somewhere around 555 degree centigrade. So, then in between any temperature you can say that the alloy melt is partially solidified and it is present in the mushy zone. So, this temperature gap has been defined as mushy zone. Okay. So, where solid liquid coexist simultaneously, and so so then the the microstructure formation and defect generation during solidification mostly control the mechanical properties of the fabricated solidified components. The shape, size, spatial distribution of different phases notably influence the physical properties of the material. Hence, it is very important to understand the and to investigate the microstructure evolution, and phase field model can serve as an effective tool to predict the microstructure of the solidifying melt while undergoing casting. So, the choice of appropriate processing parameters and alloying element plays also a crucial role in tuning the microstructure of the product material. So, that is what I was telling earlier. So, the phase field model can predict the effect of process alterations and also the effect of alloy chemistry. So, that is discussed again over here. So, therefore, it is possible to design processes and develop newer alloys targeted to specific applications, whereas a large number of trial and error that is needed in case of experimentation can be avoided. So, like we discussed in case of CFD based process model development. So, in case of this mesoscopic phase field phase field based microstructure model can also significantly reduce the time, cost and energy involved in case of trial and error kind of experimentation. Rather, it can basically provide deep insight into the the physics of the phase transformation, and also it can predict the the process condition that are needed to be adopted to achieve the desired quality characteristics, desired microstructural morphology. So, one thing has to be made clear here, that phase field model is not only limited to the prediction of phase transformation during liquid to solid transformation, rather it can also be utilized for phase transformation modeling and microstructure evolution modeling during solid state processing and also during heat treatment processes. So, phase field modeling can be utilized as an effective tool to gain insight into the physics of the process, impact of the process condition as well as the alloy composition on microstructure evolution, and also it can serve as a handy process control tool which can be implemented utilized for optimization of the process variables as well as alloy composition. So, it can serve both the purposes. So, phase field method has emerged as a very effective tool to predict microstructural evolution in solidification processes in last decade or so. And microstructures has structural and compositional inhomogeneities which may be of the following form, such as phases of different composition and crystal structure, grains of some same phase having different orientations, and domains of different electric polarization, domains of different magnetic polarization, defects, etc. Okay. So, reduction of free energy is the driving factor for microstructure evolution that is considered to simulate the microstructure evolution adopting phase field model. So, classically the growth of a single crystal from a pure melt is described by Stefan problem expressed using the following equations, which is T dot is equal to alpha grad square T. Okay. So, basically T dot is nothing but dt dt. So, that is I mean temporal evolution of the temperature, and x bar equivalent to I mean gamma Ls, that is the domain across time, and then rho L V n is equal to K S grad T S n bar minus K L grad I mean bar T L n bar. That is the second equation, and then the third one is T is equal to T m minus sigma T m by L k minus V n by mu. So, now what these terms stands for in these equations. So, in these expression that we have just discussed in the previous slide, T is the temperature of the system, I mean the melt system, omega Ls represents the regions of solid and liquid phases separated by the interface, that is delta omega. K stands for the thermal conductivity in the second equation. So, I mean, so this is what is K. So, this is thermal conductivity of the solid Ks, and Kl is the thermal conductivity of the liquid phase. Okay. Yeah. So, I mean then so the K stands for thermal conductivity, rho represents the density, and capital L represents the latent heat of fusion, whereas V n is the velocity of the interface in normal direction, and n cap represents unit normal to the moving interface. Okay. Unit normal to the moving interface. Interface is what? That is solid liquid interface. Solid liquid interface, that means the interface building on in the I mean solidifying melt, if we consider the melt. So, then the solid is evolving and the solid liquid interface is also I mean evolving with time. So, T where T m is the melting temperature, K is the capital K is the interface curvature, and sigma is the surface tension, and mu is the I mean interface mobility. Okay. So, the first equation here represents the heat diffusion in solid and liquid phases. The second equation represents the I mean Stefan condition. Okay. Yeah. So, the second equation is represents the Stefan condition, and relating the velocity of the interface, that is V n. So, we are talking about velocity of the interface, and relating the velocity of the interface in normal direction with the difference of temperature gradient across the solid liquid interface. The third equation, that is this equation where we are talking about calculating the temperature at any given moment. So, the third equation is for the Gibbs-Thomson relationship, which shows the change of melting temperature at the interface due to capillary and kinetic effects. Okay. So, here so this is the change of melting temperature, as we know that T m is the melting temperature, and how it is changing in the interface. Due to the capillary and kinetic effects, where mu is the mobility, interface mobility, that is the kinetic coefficient, and sigma is the surface tension, which speaks about the capillarity. Okay. So, moving ahead, so when the melt temperature drops below melting temperature, the solidification can be initiated by a seed particle. Latent heat is released at the interface as the crystal grows. So, higher heat is released when the surface area of the solid is high, and which in turn enhances the crystal growth. However, the higher surface area is associated with higher amount of surface energy. The effects of surface energy is to minimize the surface area. So, these two competing effects stabilizes the crystal growth. Okay. And then during alloy solidification, heat and solute both are rejected at the solid liquid interface, as we have discussed several times earlier. So, while the solid grains are growing within the bulk liquid, so that time it is basically rejecting the solutal silicon, because the diffusion ability of diffusion of the solute atoms in the solid is much lesser than into the liquid. So, that is why if we are taking the example of a typical binary aluminum silicon alloy. So, then these are the grains which are growing are alpha aluminum grains, and then it is the solute which is getting rejected, these are solutal. So, that is silicon. Silicon serves as a solute in this case. Okay. So, so this is what I mean. So, so here this is what is talking discussed about. So, during alloy solidification, heat and solute both are rejected at the solid liquid interface by the growing solid. Therefore, heat and solute diffusion both influence the grain growth in alloy solidification. In sharp interface model, microstructure evolution is tracked from the displacement of the sharp boundary, separating structural and compositional inhomogeneities. So, this approach is very complicated and becomes impractical for 3-dimensional systems. So, however, in the phase field model, so it is not a sharp interface model, rather it is a diffused interface model, which is considered where the diffused interface is considered between two neighboring grains. So, the phase field model converges to sharp interface model at some limit. So, I mean so in phase field model the microstructure is described using a set of conserved and non-conserved field variables which are continuous across the interface. The description of the model starts from the expression of the free energy of the system. So, a generalized form of free energy functional of a system can be expressed in the following way, which is shown over here. So, F is equal to integration of so it is function of C1 C2 dot Cn. So, the different chemical concentrations plus summation of I is equal to n alpha I grad C I square plus summation of I is equal to 1 to 3, j is equal to 1 to 3, k is equal to 1 to p, beta I j grad I n k eta k grad j eta k dv plus double integral g r minus r prime dv prime. So, in the above expression f small f represents the local free energy density, which is a function of conserved field variables, that is C I concentration, and non-conserved variables, that is eta k, where alpha I and beta I j are the coefficients. The first volume integral represents the local contribution to free energy, and the second integral represents the non-local contribution which may arise due to the long range interactions such as elastic interactions, electrostatic interactions, etc. Okay. So, so the gradient terms contribute the interfacial energy and have non-zero values only at and around the interface. Okay. So, so it is to be mentioned here that the difference among various phase field models arises from the definition of free energy functional. Okay. So, like R. Kobayashi developed a model for dendrite growth in solidification process for a pure substance. The model was developed by modifying Stefan's problem of solidification, replacing the sharp interface by a diffused interface. So, the field variable was taken as the phase field variable, that is say phi x bar t, that is function of both space and time, the phase field variable which distinguishes the phases. So, here phi is equal to 1 represents the solid phase and phi is equal to 0 represents the liquid phase, and the value of phi the transitions between 0 to 1 when the when it is moving from the liquid phase to the solid phase. So, that is why also it is called as a diffused interface, because the transition of the phase field variable phi from 0 in liquid to 1 in solid happens over a diffused interface of thickness eta. Okay. So, so Kobayashi scheme consists of two partial differential equations. One is the diffusion equation for temperature field T, which is again function of space and time, and the other is the time evolution of the phase field phi, phase field parameter phase field variable phi, which is the function of again space and time x bar t. So, in the model description, a double well form of free energy density is used. So, f phi is equal to 4 delta f phi square 1 minus phi whole square. So, the minima of free energy is achieved at phi is equal to 0. Okay. That means phase field variable phi value is 0 or phase field variable phi is equal to 1, depending on whether the temperature T is above the melting temperature Tm or below the melting temperature Tm. Okay. So, So the next step, I mean, so when so if I further clarify it, so phi is equal to 0 means I mean temperature is above the melting temperature, because as we have discussed above that phi is equal to 0 when the phase field parameter is in the liquid phase, and phase field parameter is equal to 1 means it is in the solid phase. That means of course the temperature is below the melting temperature Tm, then only solidification will happen. So the next step in the progress of phase field model is the consideration of alloy solidification. The phase field model for alloy solidification was proposed by Wheeler, Bottiger and McFadden in 1993. So in their description, the free energy is dependent on both concentration as well as phase field. So I mean, so you can very well understand the concepts of sharp interface and diffused interface from this slide. So a phase field model is typically a diffused interface model, where I mean phase field parameter phi changes its value from 0 in liquid to I mean 1 in solid, and in between the interface where the phase field parameter changes from 0 to 1, it is the diffused interface, that is what marks the boundary between the I mean liquid and solid, or rather it is marks the interface between the solid and liquid phases. Okay. So the phase field model for a multi-component multi-phase alloy solidification is presented in the in this following sections. So in multi-phase field model, separate phase field variables phi alpha are considered for each grain of each phase, though the time evolution of phi alpha are derived from a free energy functional f, which consists of interfacial free energy and chemical free energy as given below. So I mean so this is basically the equation is in this slide. So you can see, so the expression of interfacial and chemical free energy are given by these two expressions. So FIF corresponds to the expression of interfacial free energy, and FCH corresponds to the chemical free energy. Okay, and the relevant expressions are shown here. So here this expression so I mean expresses the free energy functional f over the simulation domain omega. So I mean, so in equation 1, so that is so I mean so the FIF stands for the interfacial free energy density and FCI stands for the chemical free energy density. So hence brackets represents, so these are the second brackets which is shown over here. So this second brackets represents I mean all the variable phases alpha within the simulation domain, whereas C alpha bar stands for generalized phase composition field for phase alpha. Okay. And if I come back to these two expression of free energy, interfacial and chemical free energy functional. So here capital N represents, so capital N is basically this one which is shown. So capital N represents the number of phases available in the system, where Vm stands for the molar volume. Okay. So this is the Vm stands for the molar volume, and the symbols alpha beta stands for different phases that are evolving within the solidifying melt. Okay. And sigma alpha beta and eta alpha beta represents the interfacial free energy and thickness of the interface of alpha and beta respectively. Whereas C bar represents local multi-component composition and mu bar represents multi-component diffusion potential of the system, and mu alpha bar is the diffusion potential for phase alpha, and G alpha is the molar Gibbs free energy density of phase alpha. Okay. So here it is assumed that mu alpha bar is equal to mu alpha. That means, so diffusion potential for is generalized across phases. So that is why it is written as mu alpha bar is equal to mu bar. So the basic equation relating the temporal variation of phi, the phase field parameter, with the free energy functional capital F, which is the summation of chemical as well as interfacial part of the free energy, is the following. So phi alpha dot is equal to summation of beta not equal to alpha to n pi square by 8 eta n mu alpha beta into delta f by delta phi alpha minus delta f by delta phi beta. So here mu alpha beta is the kinetic coefficient in Gibbs-Thomson equation, which is replaced by an effective mobility term m alpha beta, considering a diffused interface between the phases or grains of alpha and beta. So So, in the present phase field approach, the motion of grain boundaries or phase interfaces are captured using a set of coupled partial differential equations. So, obtained using the above equations, which can be represented by the following equations. So, here we can rewrite the expression, that is phase field parameter for the phase alpha, and phi alpha dot is equal to summation of beta not equal to alpha is equal to 1 to n m alpha beta in third bracket sigma alpha beta, that is the that is we have discussed. So, it is the interfacial free energy sigma alpha beta into phi beta grad square phi alpha minus phi alpha grad square phi beta plus pi square by 2 eta square into phi alpha minus phi beta plus pi by eta root over phi alpha phi beta into delta G alpha beta. So, there here G capital G is the free energy. So, the thermodynamic driving force is a function of local multi component composition C bar and melt temperature T. Okay. So, so in equation 5, so that is what is marked over here, the delta G alpha beta is the thermodynamic driving force, that is the free energy change, the expression for which is given below. So, delta G alpha beta is equal to 1 by V m, that is the molar volume, into G beta C beta bar minus G alpha C alpha bar minus mu bar C beta bar minus C alpha bar. So, the diffusion potential is related to the molar Gibbs free energy density by the following equation, which is termed here as equation 7. That means, so diffusion potential mu alpha is equal to delta G alpha by delta C alpha I. So, then thereafter equation 8 depicts the function which plays the role of focusing the thermodynamic driving force into the interface center. So, which is written as W is equal to pi by eta, eta is the interface thickness between solid and liquid phases, root over alpha root over phi alpha phi beta. So, these are the phase field parameters for alpha and beta phases. Okay. So, in the case of sharp interface models, phases present within the computational domain remains independent to each other, whereas the present phase field model adopts a diffused interface approach, wherein the interface is described as a mixture of overlapping phases. The below mentioned equation, equation 9, shows how the local concentration C bar x bar comma T at the diffused interface is related to the phase concentration C alpha bar x bar comma T. Okay. So, C bar x bar T is equal to summation of alpha is equal to 1 to n phi alpha phase field parameter, phase field variable for phase alpha, which is a function of space and time x bar comma T, C alpha bar. So, again which is a phase concentration, which is again a function of space and time. So, x bar T. So, the set of diffusion equations k equations for a total of k number of components adopted in the present phase field model can be represented by the following equation, which is marked as equation 10, where C bar dot is equal to grad bar summation of alpha is equal to 1 to n phi alpha phase field parameter for phase alpha, d alpha diffusion coefficient for phase alpha, so the and grad bar C alpha bar. Okay. Here D represents the diffusion matrix. Okay. Yeah. So, so in real system, the crystal nucleation from melt occurs mainly by heterogeneous nucleation, because it is as we have discussed in detail when we are discussing about the casting solidification module of the course, that we deliberately promote heterogeneous nucleation, so that we can get fine grained morphology in the solidified structure. So, the different factors such as walls of container, molecular impurities, floating particles, dirt in the melt act as heterogeneous nucleation sites, or seed particles for crystal nucleation. So, in these sites the nucleation barrier gets reduced significantly and hence have higher nucleation rates. Two different models are used to consider the heterogeneous nucleation in phase field simulation as discussed below. So, nucleation model. So, there are two kind of nucleation models that are being implemented for the present phase field model that is discussed with you. So, so these are seed density based model and seed undercooling model. So, there is a primary difference in these two models is that in case of seed density model, we already assume that there are a certain number of seeds particle or nuclei already present in the solidifying liquid melt, present in the solidifying liquid melt. And in case of this seed undercooling based model, so in this case it is totally the nuclei formation, so nuclei formation gets activated, nuclei formation nuclei formation gets activated based on the temperature of the melt. So, that means it depends on the undercooling available at that particular location within the melt, and that decides the activation of the seed particle or the nuclei to become fully formed grains within the solidifying melt. So, in seed undercooling model, the presence of a new seed at a location is considered when the local undercooling at that location exceeds a predefined value of critical undercooling. So, the local undercooling depends on the local temperature and the critical undercooling value generally depends on the solid liquid interfacial energy, that is sigma Ls of the nucleating phase, the entropy of fusion and also on the nucleating agent. So, the expression for critical undercooling obtained from Turnbull's free growth condition is given by the following expression. So, delta T n, that is the critical undercooling necessary for seed undercooling model, is equal to 2 sigma Ls, that is the interface energy of the nucleating phase, divided by delta S, that is the SLS, that is the entropy of fusion of the nucleating phase into R. So, where R is the seed radius, whereas in case of seed density model, the density of seeds, that is nucleation sites for a particular phase in the simulation domain are specified. The nucleation is checked at these predefined nucleation sites only, and no other sites nucleation is possible where seeds are not defined. And so, this is the difference between the two different nucleation models that are considered in case of phase field model that is discussed with you today. And the global temperature evolution of the system can be expressed by the following expression, that is T dot is equal to 1 by Cp bar into 1 minus Q dot by V into dt plus summation of alpha H alpha F alpha dot, where Q dot by V represents the rate of heat extraction per unit volume and H alpha is the enthalpy per unit volume of phase alpha. Cp bar is the specific heat averaged over the cells of the numerical grid, that is capital N x y z, and F alpha dot represents the average rate of change of phase alpha with time. Okay. So, F alpha dot is equal to nothing but ddt of alpha, ddt of F alpha. Okay. So, that is the phase fraction, I would say, and so the change of phase fraction of alpha phase with time is depicted as F alpha dot. Okay. So, in the present phase field model, the solid phases are characterized as isotropic or anisotropic. So, for anisotropic phase, the nature of interfacial free energy and mobility are anisotropic in nature, that is the values of the parameters varies with direction of interface normal. So, for a phase having cubic symmetry, anisotropy of interfacial stiffness, that is A sigma n bar is equal to 1 minus delta sigma cos 4 theta, and anisotropy of interfacial mobility A mu n bar is equal to 1 plus delta mu cos 4 theta. So, here delta sigma and delta mu are the static kinematic and so here delta sigma and delta mu are the static and kinematic anisotropic coefficients respectively, and theta is the Euler angle of the grain orientation. So, it is to be noted here that the interfacial stiffness sigma asterisk is related to the interfacial energy sigma by the following relationship. So, that is interfacial stiffness sigma asterisk is equal to interfacial energy sigma plus d2 sigma by d theta 2. Okay. So, so this is how the the phase field model looks like. So, so now we will discuss about the boundary condition. We will also take up a typical problem and we will discuss about the different nuances, how the findings can be obtained. So, the boundary conditions. So, so this is the typical domain bound which is considered for a 2D phase field simulation of solidification microstructure formation of a novel AL 15 Mg2Si and 4.5 Si composite that is developed within our group, and it is also I mean granted 2 Indian patents are granted on this composite. Okay. And also there are several publications which are online. Interested I mean readers may please go through those articles to gain further deeper knowledge about the developed composites and its mechanical and physical attributes. So, coming back to the phase field model that is developed for this composite to predict its microstructure evolution. So, starting with the convection and cross diffusion. So, not considered in the current phase field model, cross diffusion coefficients and complete diffusion matrix become essential for slow solidification rates or ternary or higher alloy systems, neglected in the present aluminum XMG2Si YSY composites due to their fast solidification rates within the metallic molds, and similar specifications were also adopted in prior studies reported in the literature. And so, number 2, simulation details. So, simulation has been performed using a Micres software, which is the phase field solver that is utilized to develop the present phase field model and to simulate it. Simulate the microstructure evolution for this class of AlMg2Si composites with extra silicon, and so the purpose is 2D simulation of solidification microstructure formation of the composite and computational domain that is already shown in this slide. So, and then references for model description. So, studies provide detailed explanations of the PF model. So, the areas for further improvement of the developed models are coupling the 2D simulation with macroscopic temperature fields and also fluid flow field. So, these are like future improvements that are possible. So, so this is basically the typical simulation domain, 2D simulation domain that has been considered. So, you can see a square of 100 cross 100 micrometer domain, which is of course a micro domain, and because we are talking about microstructure evolution simulation here using the adopted developed phase field model, and so yeah, and also the concentration values are shown, that is CL at boundaries, that is at y is equal to 0 and at y is equal to 100. It is defined as the liquid concentration, solute concentration in liquid is same, that is CL. Okay. And so these are some of the results. So, it is showing the solidification sequence of the Al15 Mg2Si 4.5 Si composite, and you can also see that how a typical animation is shown over here. So, you can see that how these solid particles are evolving in the melt and then they are growing. So, these are this greenish phase is the Mg2Si particulates. So, these are the ceramic reinforcement that are generated in situ within the melt during solidification, that is reaction of the pure magnesium and the extra silicon present within the composite matrix responsible for this reaction and generation of Mg2Si particulates, and once the Mg2Si is formed, then it serves as a heterogeneous nucleating agent for alpha aluminum. So, this white phase is nothing but the alpha aluminum. So, why we are calling here both Mg2Si and alpha aluminum as primary phases, because Mg2Si is the first phase to nucleate out from the solidifying composite melt, and aluminum being the dominant phase, that is why we are calling aluminum also as primary. So, here you can see that there are 2 primary grains that are evolving from the composite melt, and then in the solidified microstructure of the composite we see 3 distinct phases. Number 1 is the Mg2Si particulates, number 2 is the alpha aluminum grains engulfing the Mg2Si particulates, and number 3 is the silicon eutectic phase. So, this eutectic here it is basically a combination of aluminum, Mg2Si and solutal silicon. So, it is the eutectic mixture of both all 3, that is the eutectic phase that is shown here as the deposited in the boundary, in the grain boundary of alpha aluminum as well as primary Mg2Si grains. Okay. So, I mean so this is the typical example. So, that is what is shown in case of solidification of a composite that is developed within the scope of our group, and to give you an understanding about the phase field model, its applicability and how it can be implemented to simulate the real life microstructure evolution process for a typical composite or alloy, or even it is applicable for pure metals. So, yes, and that is how you can understand that this model can be useful to grab insight into the physics of microstructure evolution, and also it can be I mean useful for I mean optimizing the process condition, so that it can be I mean utilized for I mean prediction of microstructure and tuning the process variable accordingly, so that I mean the desired quality characteristics in terms of the desired shape, size, morphology, and I mean and also the I mean the mechanical properties in the solidified parts can be achieved. So, you can see that here from we can predict the microstructure evolution, and also we can I mean nullify the number of experiments, and also we can tune the process condition and alloy composition to get the desired microstructural attributes in the solidified object. So, then you can understand that we can basically do microstructure engineering here, so that we can derive the desired mechanical as well as functional properties in the solidified parts. Okay. So, now if we discuss about a typical phase field model for defect generation. So, I mean like porosity is a critical issue that we have discussed during casting, and also we have discussed during welding. So, because I mean porosity is generally happens in the solidifying mush due to the I mean gas absorption, and also entrapment of gases like hydrogen in case of lighted metals like aluminum, magnesium, and so the entrapment of this gaseous evolution causes bubble formation and thereby formation of porosity. So, I mean so reason of appearance of porosity during casting are contraction during solidification, and number 2 is evolution of dissolved gases from the molten metal. Okay. So, it will be clear from this graphical present. So, you can see here that here the pore nucleation temperature, the gas concentration of liquid Cl is higher than the maximum solubility Cl max of gas in liquid. So, I mean so the I mean gas concentration in liquid is I mean basically I mean is decreasing. I mean it is decreasing with the increasing temperature. That means the actual content is decreasing, that although the Cl max, the maximum solubility which is increasing with temperature. So, the difference between these two limits, that is maximum solubility limit at that particular temperature, and the actual gas concentration present in the liquid, which is defined as Cl, is shown that this is the concentration which is I mean evolving as porosity within the I mean solidifying melt. Okay. So, I mean so the assumptions for the phase field model, large volume change is associated with evolution of gas phase. So, therefore, the volume change due to gas phase evolution will be considered in the present phase field model. So, the change of melt pressure due to the shrinkage and growth of gas bubble will be considered in the thermodynamic description within the Gibbs energy equation. Okay. So, in general the molar volume of different phases is assumed to be same in the present PF model. So, that means molar volume of any phase alpha, that is V alpha, is equal to V. That means whether it is alpha or whether it is beta, all the phases molar volume is assumed to be equal, that is V, and the volume change associated with phase change is considered as 0, that is I mean dV x bar is equal to n x bar d summation of alpha phi alpha x bar V alpha is equated to 0. Okay. So, V x bar is the overall volume at x bar, n x bar represents the number of moles at x bar, and V x bar is equal to n x bar summation of alpha phi alpha phase field parameter of phase alpha into x bar, which is function of x V alpha. So, V alpha is the nothing but the I mean molar volume. So, consider that hydrogen is dissolved into a liquid metal in supersaturated condition. So, at that time it has very small contribution to overall volume. However, when the hydrogen comes out as gas bubble, large volume expansion takes place. Therefore, the volume change due to gas phase formation cannot be taken as 0, although we have considered the volume change due to phase transformation. For example, liquid to solid phase transformation is considered as 0 in the previous slides. Okay. Yeah, this is what we have discussed, but that cannot be the same when we are talking about evolution of porosity. That means, evolution of gas bubble, or gas phase formation within the solidifying liquid melt. So then in that case dVx cannot be equated with 0. So that means it is not equal to 0. So the change of volume is balanced by introducing a continuity equation in phase field description. The continuity equation considers the conservation of total amount of matter. So so the continuity equation is as such. So del T n of n x bar plus divergence j equated to 0. So average molar volume V bar is equal to summation of alpha phi alpha x bar into V alpha. So so which gets further simplified. The above expression we can get del T of V x bar by V bar, okay, plus divergence j bar is equal to 0. Okay. So here 1 by V bar del V del T plus divergence j bar is equal to n x bar by V bar del V bar by del T. So it can be interpreted as volume production term. So considering a volume flux j bar prime is equal to V bar into j bar, the above equation gets further simplified into del V x bar by del T plus divergence j bar. So then like we have to and then is equal to n x bar. So here V bar, that is the volume production term, it gets cancelled in both left and right hand side, and so then it becomes, so this equation gets simplified to this expression. So del V del T plus divergence j bar is equal to n x bar del V del T. So again V bar is written here as summation of alpha phi alpha x into V alpha. So V bar is expressed like this. So the volume flux is approximated by a diffusion like equation here. So j bar prime is equal to minus dV grad V. So here where dV is the diffusion coefficient, diffusion matrix, I would say, is equal to summation of alpha d alpha V phi alpha V is the transport coefficient. So it is to be mentioned that the diffusion equation ensures a redistribution of excess volume by locally redistributing matter via the flux, diffusion flux j bar prime. Okay. So the chemical driving force for or Gibbs free energy of the different phases are obtained from Calvert database. An analytical term is added to the molar Gibbs free energy function G to consider the effect of change of pressure due to growth of gas bubble or shrinkage of matrix phase. So which is depicted below, considering an ideal gas. So G gas P function of pressure and temperature P T is equal to G gas, that the Gibbs free energy function P 0 some function of capital T plus summation of plus integration P 0 to P V d P is equal to G gas P 0 T plus integration P 0 to P. So as we know that P V is equal to R T if n is equal to 1. So then V is equal to R T by P. So that is what is shown over here. So then integration P 0 to P R T by P d P. So it can be further simplified as G gas P 0 function of temperature plus R T, it comes out of the integration. So d P by P, that is ln P, that means ln P by P 0. So this is the resultant expression of the Gibbs free energy. So this is basically the typical phase field formulation that needed to be considered for simulating porosity formation. So this is a brief idea about how we can also simulate along with microstructure the formation of porosity within the evolving solidifying microstructure in case of both casting as well as welding. So with this we are done with the phase field modeling of the solidification microstructure formation during casting. and also the same principles are applicable in case of welding too. And so, we will start with the new module in the next class. Thank you.